So we are dealing with the second example in this segment, which is circular motion segment, and we are dealing with problem number 1.37. Here the problem is asking us, a point moves along a circle with velocity v equals alpha t, where alpha equals 0.5 meter per second square. Find the total acceleration of the point at the moment when it covered the nth fraction of the circle after the beginning of motion. Here n equals 0.10. So as we start solving this problem, let us begin with what is given in the problem. So given in the problem is velocity v equals alpha t, and alpha is 0.5, that is given to us, meter per second square, and it is asking us to find the total acceleration when it has covered the nth fraction of the circle, and the value of n is equal to 0.10. So what we need to understand is what exactly the problem is asking us to do. So we consider something like this, that the particle is moving in a circular path which is like this. Now if I look at this velocity expression, so if we put t equals 0, then the velocity will be 0. So we consider that the motion starts here where t equals 0. So this is t equals 0 mark where motion commences, and when it has covered 0.1 part of the circle, so we can say over here that the motion starts and we are somewhere here, and this is a very small part of the circle. At this point, as it covers 0.1 part of the circle, it will attain a certain value of tangential velocity, which we write as Vt. And at this point, we will have two acceleration. Due to velocity, we will have a radial acceleration v square upon r. And along with that, we will also have a tangential acceleration because of the changing velocity, which is written as alpha t. So hence, if we approach this problem, so we first of all calculate for the tangential acceleration. So the first thing that we are writing here is, we have two accelerations, and over here the first one that we are discussing is tangential acceleration, and the tangential acceleration is equal to dv by dt. So derivative of alpha t with respect to dt, so alpha, and this value is constant, and it is equal to 0.5 meter per second square. Now the second part is the radial acceleration. So second part is radial acceleration. In order to understand this radial acceleration, the formulation says that the radial acceleration is equal to v square upon r. So we need to know the velocity after it has covered 0.1 part of the circle. So over here we start to approach the problem to evaluate this part. So over here we say that after t equal to 0, the initial velocity is equal to 0, and the v square is equal to u square plus 2 tangential into displacement. So over here we write v square equal to 2 a tangential into displacement, and over here what is important is to understand that the distance covered, that is s, is equal to 0.1 part of the circle, which is 2 pi r. So 0.1 part of the circle, which is equal to 2 pi r, and over here we get 0.2 pi r. So if we put this value here, then we can say that v square equals 2 alpha, which is tangential acceleration, which we have already evaluated, and this one is 0.2 pi r, and hence on solving we obtain 0.4 pi alpha r. So this is the value of v square that we have evaluated, and therefore the radial component of acceleration, which is v square upon r, so this can be written as 0.4 pi alpha r divided by r. So we get 0.4 pi alpha. So we have two component of acceleration, one radial component and the another is tangential acceleration, and hence a net can be written as a radial square a tangential square root. So a tangential and a radial squared, so we have 0.4 pi alpha squared plus alpha squared square root, and on putting the value of alpha, which we know as 0.5 in the problem, we obtain the magnitude of net acceleration as equal to 0.8 meter per second square. So this is the final answer for this particular problem, and this is how we solve a problem like this. This was problem 1.37.